Hi everyone, today's lesson will be on fractional exponents. So let's begin with this do now here that I've written. I'd like you to take a minute, copy it down, and solve for n. Pause the button if you need to, and we could start again. Okay, so to solve this equation, the first one, using the rules of exponents, we know that when we multiply with the same base, we add the exponents. So this is 2 to the n plus n is equal to 2, or 2 to the 2n equals 2, which can be written to the first. So we see that 2n must equal 1, and n is equal to 1/2. So we get a very interesting result. The 2 to the 1/2 times 2 to the 1/2 is equal to 2 to the first. Okay, and in the second one, similarly, we get 2 to the n plus n plus n plus n, which is 2 to the 4n, and that means 4n must equal the exponent of 1, and n is 1/4. So we see that 2 to the 1/4 times 2 to the 1/4 times 2 to the 1/4 times 2 to the 1/4 is equal to 2. Well, in the first one, let's take a look at that. If we rewrite 2 to the 1/2 in radical form, we could write it as the square root of 2 times the square root of 2, which we know the square root of 2 times the square root of 2 is 2. And similarly, each of these is the fourth root of 2. Which is equal to 2. So we know that the square root of 2 squared is 2. We talked about this in our last video. And the fourth root of 2 to the fourth is 2. So we have the following definition for fractional exponents. And we say, okay, so here's the definition. That if the nth root of a represents a real number and the index n is greater than or equal to 2, and n is an integer, then we define the nth root of a to equal a to the 1 over n. And that introduces the definition of a rational exponent. Note that from our previous video, when a is less than 0, our index n must be odd. And when a is greater than 0, our index n is even. Otherwise, we would get an imaginary number. So let's just assume here that we're working with real numbers. Okay, so keeping that in mind, let's compute the following. Let's compute 49 to the 1/2. Okay, I'll put this as number 3. And let's compute negative 32 to the 1/5. Okay, take a minute and do that just to make sure we have it. Okay, so the 49 to the 1/2 is the square root of 49, and that's just 7. And negative 32 to the 1/5 is just the fifth root of negative 32, and that would be negative 2, since negative 2 to the fifth is negative 32. Okay, just to make sure that we understand the notation. All right, let's move on to the next page. All right, now let's consider this. If the cubed root of 7 is 7 to the 1/3, then what does the cubed root of 7 squared mean in exponential form? Okay, so let's look at that. Cubed root of 7 squared can be written as 7 to the 1/3 squared. And using the rules of exponents, when we have a to the m raised to the nth power, we multiply the exponents. We could write this as 7 to the 2/3. But since multiplication is commutative, we could do this. 7 to the 1/3 squared would be the same as 7 squared to the 1/3, which also gives us 7 to the 2/3. So this can be written in another way. Using this form, we see that the cubed root of 7 squared is equal to the cubed root of 7 squared. So this exponent can be either moved out of the radical or be moved into the radicand. So notice the place of the exponent, which allows us to generalize our definition of rational exponents. And we have the following. Oops, wrong color again. I have to get used to this. Wait, let's get back to the colors. Definition. If the nth root of a is a real number, and m and n are positive integers, then we define the nth root of a to the m power is equal to the nth root of a to the mth power in the radicand, which is equal to a over m to the a to the m over n. So keeping that in mind, let's write an exponential form. Okay, let's do a few. So I'll call this number 5, number 6, and number 7. So number 5 is the cubed root of 5 squared. Number 6 is the 5th root of 10 to the 4th. And this is the 7th root of 2 cubed. Okay, let's take a minute and write these in exponential form. All right, let's look at the answers. So this is equal to 5. Now, the denominator of the exponent should be the index, and the numerator is the exponent here. So that's 5 to the 2/3. This one would be 10 to the 4/5, and this one would be 2 to the 3/7. And those are our answers, just to make sure we understand where these numbers go. Okay, let's move on. Okay. Now let's compute the following. All right, now let's compute -27 to the 2/3. Let's get an answer for that. Number 9, 36 to the negative 3. Oh, wait, no, sorry about that. 36 to the 3 halves. Let's make sure we know how to do that. Okay, let's do these two for now. All right, so this one would be the cubed root of negative 27, but I like to bring the exponent when I compute outside, because this way I don't have to take the root of a very large or small number. So this gives me negative 3 squared, which is 9. And here I have the square root of 36 cubed, so that's 6 cubed, and that gives me 216. So when I have to compute, or when we have to compute, it's a good idea to bring the exponent outside the radical. Okay, so we know how to do those. Now, let's move on to fractional exponents that are negative. So we're going to the next page. I know what number I'm up to. Okay, I'm up to... Oh, wait, let's just make sure 9. So we're going to start with 10. So let's look at this problem. Seven to the negative 2/3. All right. Oh, I forgot my fraction bar there. Okay. Now, when the rational exponents are negative, we go back to the rule. Remember that when we have a negative integral exponent, we take the reciprocal. So this means 1 over 7 to the 2/3. Okay, so that negative really means take the reciprocal of 7 to the 2/3. Okay, so, and again, if we think of it this way, we could rewrite 7 to the negative 2/3 as 7 to the 2/3 to the negative 1. And any number to the negative first means find the reciprocal. So why don't we keep that in mind? Let's do that. Whenever we have a negative fractional exponent, ignore the negative and then find the reciprocal of your answer. So let's take a look at these. Okay, I'll put this as 10a, 10b, and 10c. 36 to the negative 3 halves. Let's compute these. 32 to the negative 3/5. And 8/27 to the negative 1/3. Okay, let's try and computing these. Let's take a minute and do that. Okay, so let's start doing it. So we're going to get the reciprocal of 36 to the 3 halves here, the reciprocal of 32 to the 3/5, and the reciprocal of 8 to the 27th to the 1/3. Okay, so this is 1 over the square root of 36 cubed. This one would be 1 over the 5th root of 32 to the 3rd. And this one is 1 over the cubed root of 8 over 27. Now let's compute. This one is 1 over 6 cubed, and I believe that gives me 1 over 216. This is 1 over 2 cubed, and that gives us 1/8. And this one gives us 1 over 2/3, which when we go through the division gives us 3 halves. And there are the answers. Okay. All right, so we're good with that. Now let's practice rewriting a radical, or rewriting from fractional form into, or rewrite each expression into into radical form. So why don't we try it? Okay, so I had to pause there because I wasn't sure what I was up to. So the instructions now are to rewrite in radical form with no negative exponents. So I'll give you a few. Okay, I'll call this 11A, 11B, 11C, and 11D. Okay, so the first one is 2x to the negative a half compared to 2x to the negative a half, negative 8x to the negative 1/3, and the fourth root of x cubed y to the negative 4. Okay, this one didn't come out too good for me. Negative 1/3, that's negative 1/3. Okay, so let's take a minute and rewrite each in radical form with no negative exponents. All right, let's start going over this. So this negative exponent in 11a belongs only to the x. So we could write that as 2 over x to the 1/2, which is 2 over the square root of x. Whereas in 11b, the negative 1/2 belongs to the whole expression because of those parentheses. This is 1 over 2/2, which can be written as 1 over the square root of 2x. So please notice the difference between these two. Okay, in the same way as 11a, that negative 8 belongs on top, the x to the 1/3 on the bottom, so we get negative 8 over the cubed root of x. The last one can be done in many ways, but the way I approached it was I rewrote this in fractional form. So I wrote it as x cubed y to the negative 4 to the 1/4. And then using that rule that when we have multiplication in the parentheses, we could multiply each exponent by each exponent in the parentheses by the exponent outside the parentheses, I get x to the 3/4 times y to the negative 1. 3 times a quarter is 3/4, negative 4 times a quarter is negative 1. And this can be rewritten as the fourth root of x cubed. And then because this negative 1 belongs to the y, I'll bring it down here, y to the first. And that would take care of those problems. All right, let's move on. Oops, I went to the next page. Okay, let's practice writing in exponential form. Oops, I forgot my pen. Write in exponential form. The following: 12a, 12b, 12c, and 12d. Okay, the first one is the square root of x cubed y to the 5th. The next one is the square root of a to the negative 2b cubed. The next one is 1 over the fourth root of p to the 4th q to the negative 8. And the last one is, hold on. Oh, I don't have a last one. I just had 3. So, I just think I'm going to stick with those 3. I miscounted. So let me erase this last one. Okay, that's good. All right, that's good. All right, so let's write these in exponential form. Let's pause and do those 3. All right, for the first one, we can rewrite this as x cubed y to the 5th to the 1/2, which can be written as x to the 3/2 times y to the 5/2. And there's our answer for that. Okay, the next one, similarly, we could write a to the negative 2b cubed to the 1/2. And that becomes a to the negative 1, only because negative 2 times 1/2 is negative 1, b to the 3/2. And of course, that's enough, but this again could be written as b to the 3/2 over a. But we didn't need to do that in this problem. And then finally, in the last one, this can be rewritten as 1 over p to the 4th q to the negative 8 to the 1/4, which is equal to 1 over p q to the negative 2. And again, if we wanted one expression out of it, what we think of is 1 over p is p to the negative 1, right? That's p to the negative 1. And q to the negative 2 to the negative 1 just gives us q squared. So I think that's correct. Oh, I'm sorry. It should be p to the negative 1. I made a mistake again. Miswrote. This should be p to the negative 1. P to the negative 1. Okay, that's it. And that's the answer for the last one. Okay, so we're done. Let's take a look at a few other problems that are a little bit more difficult. Okay, that was our intro. Express in simplest radical form. All right, so I'm going to give these their own numbers. 13 is the cubed root of 4 times the cubed root of 4. 14 is the square root of 8 times the 6th root of 8. 15 is the cubed root of 4 divided by the 6th root of 2. I think I have more on this page. Yeah. In 16, I have the 6th root of 8 cubed divided by the 6th root of 4 squared. The next one is, 17. The 4th root of the square root of x. So now we're talking about nested radicals. And 18 is the 5th root of the cubed root of 2x. Okay, let's try those first. Take a minute, try them, and see what you come up with. Okay, let's go over these. So this one can be written as 4 to the 1/3 times 4 to the 1/3. And remember, when we multiply by the same base, the rule is to add the exponents. So here we add 1/3 and 1/3, which gives us 4 to the 2/3. And as a radical, that's the cubed root of 4 squared, or the cubed root of 16. So either one of those is correct. In the next one, we could write it as 8 to the 1/2 times 8 to the 1/6. As long as we have the same base, we could add the exponents. 8 to the 1/2 plus 1/6. We have to do a little bit of fractions here. We have to add fractions. And if we add 1/2 and 1/6, well, we have to have a common denominator. So remember that 1/2 is 3/6, and 3/6 plus 1/6 gives us 4/6, which could be simplified into 8 to the 2/3. So this is the cubed root of 8. I'll put down the square outside. That gives us 2 squared, which is equal to 4. And our answer is 4. Okay, I'm going to erase this little thing here. The bases are the same. I don't want you to get confused. Okay. All right. Now, so notice that in 13 and 14, the bases were the same. But that's not true in the next one. So let's start the same way. We'll rewrite this as 4 to the 1/3 over 2 to the 1/6. Now, in order to multiply or divide exponential expressions, the bases have to be the same. So we'll rewrite 4 as 2 squared to the 1/3 over 2 to the 1/6. And then we proceed. So that would give us, all right, I'm going to erase a little bit of this problem because I need room. Okay. So that would give us 2 to the 2/3 over 2 to the 1/6. And the rule is that when we divide with the same base, we subtract the exponents. So if we subtract 2/3, take away 1/6, well, 2/3 is 4/6. So 4/6 take away 1/6 is 3/6, which is known as 2 to the 1/2, which is just the square root of 2. And that takes care of that expression. Who would think it would come out to the square root of 2? Okay, I'm just going to make a line here so we don't get confused with the previous problem. All right, now let's take a look at 16. So in the same way, I'd like to divide, and I have to get a common base. So let's take, well, I think the easiest way to handle this is to rewrite it as the 6th root of 2 cubed, which is 8 cubed. And this is the 6th root of 2 squared, which is 4 squared. Okay, keep in mind that this is the 8. And 2 squared is the 4, right? Okay. So if we go ahead and simplify that using rules of exponents, we get the 6th root of 2 to the 9th. Remember, we multiply here, over the 6th root of 2 to the 4th. Now, we could do a lot of things from here. We could translate each one into exponential form and then divide, or we could use one of those division rules. This is the 6th root of 2 to the 9th divided by 2 to the 4th, which gives us the 6th root of 2 to the 5th, I believe, when we subtract the exponents. And that is the answer, or it's the 6th root of 32. Okay, there's so many ways to get that, as long as you get the 6th root of 2 to the 5th or the 6th root of 32, whichever way you do it. All right, now 17 is interesting. Here we have nested radicals. So we could rewrite the square root of x as x to the 1/2. And that as to the 1/4, right? Because we're writing, and again, using that power rule, this gives us x to the 1/8, which is just the 8th root of x. And we're done. So nested radicals are very interesting. This one, number 18, we've got nested radicals again, but 2x in there, but we proceed the same way. So this is the fifth root of 2x to the 1/3, which is 2x to the 1/3, and then outside of that, a 1/5. We could multiply these two to get 2x to the 1/15th, but again, the 2x is underneath the radical. So as a radical expression, it's the 15th root of 2x. And that's the answer to number 18. Okay, I hope you're beginning to feel a little bit more comfortable with these fractional exponents. All right, let's try some more. Let's move on to the next page. We were up to number 18. Okay, now this is number 19. Okay, 19, I gave one year to my class, and I found it really challenging. I want you to write as a single radical expression the sixth root of ab squared times the cubed root of a squared b. See what you come up with. That one is a little bit more complicated than the others, but I wanted to put that into our notes. So pause and try it. A single radical expression. Okay, so what I do is I just take the ab squared, raise it to the 1/6, and the a squared b, and raise it to the 1/3. Then, using the rules of exponents, I bring the 1/6 over and multiply when I can. So I get a to the 1/6 b to the 2/6 times a to the 2/3 and b to the 1/3. And this is all multiplication. So we could rearrange the terms, not the terms, but the variables using the commutative property. So we get a to the 1/6. Oh, wait, I think I meant this to be a b, didn't I? Here I go again, making another error. Okay, so this should be a b, my mistake. So it's a to the 1/6 times a to the 2/3. The b to the 2/6 I'll write as b to the 1/3 times b to the 1/3. Now we add when we multiply with the same base. So this is a to the 1/6 plus 2/3 times b to the 1/3 plus 1/3. So a little bit of arithmetic. 1/6 plus 2/3 is 1/6 plus 4/6, which is 5/6, I believe. So this is a to the 5/6 times b to the 2/3. But we want a single radical expression. And to get a single radical expression, we have to get a common denominator. So we could pull those factors together. So we'll rewrite this one as b to the 4/6. Keep the other one. I believe that is correct. And we could think of this as the sixth root of a to the 5th times the sixth root of b to the 4th. And because the indices are equal, we can multiply the radicands. So we have the sixth root of a to the 5th, b to the 4th. And that would be the expression as a single radical. That one was hard. That one was really challenging. Okay. All right. Now, I think that takes care of it. Again, I'd like to give you a few just to make sure that we understand it. So this last exercise is to simplify and give answers in exponential form. Okay, and I wanted you to try these. 20. The square root of x times the cubed root of x times the sixth root of x. Okay, and then this one, 21. The cubed root of a squared times the cubed root of a to the 4th. All right, that one isn't too bad. I have another one, which I will put on the next page once we're done with these. Okay, so let's try them. Okay, so to do number 20, we write this as x to the 1/2 times x to the 1/3 times x to the 1/6. We have the same base. We add the exponents, x to the 1/2 plus 1/3 plus 1/6. And when we do that arithmetic, we have 1/2 plus 1/3 plus 1/6 is equal to all over 6, 3 plus 2 plus 1. That gives us x to the 5/6. That's a 5, actually. That's a very bad 5. Wait, let me just make that clearer. X to the 5/6, which is the 6th root of x to the 5th. Or to the 5th on the outside, whichever one you like. And that takes care of that one. Oh, wait, did I do that correctly? No, that's wrong. This is 6/6, right? 5 plus 1 is 6. This is equal to 1. Oh my goodness, I can't add anymore. So I should erase this number. Ooh, boy. Let's just erase that. And the answer is just x, period. So let's put, excuse me, let's put a box around that. I misadded. I'm sorry about that. Okay. In the next one here, I could write this as a to the 2/3 times a to the 4/3, and I just add the exponents. I get a to the 6/3, which comes out to be a squared. That one was a nice one, nice and easy, and I think that one's correct. Let me just check my notes. Yeah, that's correct. All right, let's go on to the next page. Oh, I have to add a page. Up to number 21. Okay, this is 22. 22. The 4th root of x times the 6th root of x divided by the cubed root of x. Okay, that's my last problem. And also, just to tie it all together, I'd like you to find the number x that makes this equation true. And this is the square root of 8 times the 5th root of 4 is equal to 2 to the x. All right, and that's our last problem. That ties it all together. All right, take a minute, do those, and we're done. Okay, let's do number 22. So, this is written as x to the 1/4 times x to the 1/6 divided by x to the 1/3. So here we have a little bit of multiplication and division. We are multiplying with the same base, so we add x to the 1/4 plus 1/6 divided by x to the 1/3. Now let's see if I could get this right this time. 1/4 plus 1/6 has a common denominator of 12. So this becomes 3 plus 2. That is 5/12, if I'm correct. I hope so. X to the 5/12. And this is x to the 1/3. And when we divide with the same base, we subtract the exponent. So we have x to the 5/12 minus 1/3. So let's do that on the side. 5/12 minus 1/3 has a common denominator of 12. That's 5 minus 4. That's 1/12. So that's x to the 1/12. And as a radical, this is the 12th root of x. Okay, that was tough. Well, not tough, but tricky. Now, this is the last problem I got from Math Counts competition. And it kind of ties in everything that we've discussed today. Notice that we have an index of 2 here and an index of 5 here. And we have to rewrite this as a base of 2. So our first step is to rewrite the radicands as a base of 2. So let's write 8 as 2 cubed. and 4 is 2 squared. So at least it looks alike. Now we'll write this into exponential form. This is 2 to the 3 halves times 2 squared to the 1 half, or should I say, this is really, make it clear, 2 cubed to the 1 half, which gives you this. And this is 2 squared, oh no, not to the 1 half, to the 1/5. Oh, just erase that, make it 1/5. Okay, that's better. So this should be 2 to the 3 halves times 2 to the 2/5 equals 2 to the x. And just like the do now, if the bases are the same, we add the exponents. So this is 2 to the 3 halves plus 2/5. So we have to add this on the side. 3 halves plus 2/5 has a common denominator of 10. So we have to multiply the 3 by 5, we get 15, and we multiply the 5 by 2, and we get 4. Let's see, I just want to make sure I'm doing this right. I just hope I'm right here. Okay, I think so. And this gives me 19 over 10. A little crazy, but that's what it gives me. So this gives me 2 to the 19/10 equals 2 to the x. So equating the exponents, x equals 19 over 10. All right, so that takes care of our lesson on fractional exponents. I tried writing horizontally this time so I could take up the page, but I noticed I used more pages. All right, so have a great day and thank you for listening. Oh, and before I forget, hold on.